Hi everyone, and welcome to the Learn Solidity in 15 minutes for the Harmony One blockchain tutorial. Today, we will learn about deploying a smart contract onto the Harmony One blockchain, and then we will learn about different constructs that make up a Solidity smart contract, the different operators, relational, logical, arithmetic, the different data types and data structures, contracts, different nuances that make up the Solidity language. So without further ado, let's begin. So let's start by deploying and interacting with a sample Solidity smart contract. So what we have here is a simple bank example, which will just demonstrate some of the functionality of a smart contract, which includes some of the data types, functions, being able to transfer and deposit one tokens, and being able to see your balance. So very quickly, we just hop over into the Solidity smart contract. We go into the compile tab, and what it's doing is it's compiling the smart contract and storing the results onto your browser. You can go into your deploy tab and actually deploy this. So in this example, we are using the JavaScript virtual machine, but you can quite quickly change it into an injected Web3 or Web3 provider. Assuming that you have a MetaMask installed, you can actually just flip through this and deploy onto an actual blockchain with some configuration. So we'll just quickly deploy this smart contract, and then we will test out some of the features. So let's have a look at our balance. Currently we have 0. So if we try to withdraw 0 from a 0 balance, it'll throw an exception. It'll just revert because it will say that you don't have enough balance. Now we will deploy some way into this account. So if I check the current balance, we have 0. Just click the deploy button, which will actually send some 1 tokens to the smart contract through its payable function called deposit. Now if I check the balance, I'll have 10 way. If I click the withdraw button now, I can actually withdraw that 10 way out of that smart contract. And if I look at the balance now, I'll have 0. Now that's just a very simple smart contract that we deployed into the Java virtual machine that's running on your environment, emulating a blockchain. So let's hop back over to our slides, and we'll start talking about the different constructs that make up the Solidity language. So the most basic construct of any programming language are the data types and the data structures, and this is no different for Solidity. In Solidity, there are primitive types and non-primitive types. Primitive types are the numericals, the bytes, the strings, the bills, and address. In Solidity, there are no floating point numbers. So all numeric values must be represented as a signed or an unsigned integer. You can also explicitly define the size for the unsigned and unsigned integers in factors of 8. So for example, you in 8, 16, etc. For data structures, there are linear data structures, which can be both dynamic and static arrays, and non-linear ones such as mappings, structs, and enumerations. Data structures can be nested, and you can also specify the data location of the data structure. Either it's in storage, memory, or in core data. All data structures and primitives can be deleted. So let's hop over to some examples of data structures in Solidity. Solidity supports uints and integers only. There's no doubles or floats. Date and time variables are stored as integers. You can have constant, and the compiler will replace the name of the constant with the actual value at compile time. By default, any variables defined in a contract are internal, which means it can be accessed only by the contract and its derived children contracts. If you want to change the visibility, you have to explicitly specify that as part of the arguments. Prior to 0.8.0 of the Solidity language, you had to worry about overflows. So you had to have special checks in place to make sure that when you add, subtract, delete, or multiply certain variables, that they don't overflow. OpenZeppelin Safe Math actually helped you to do that. However, after 0.8.0, the compiler and the runtime will actually throw an exception and revert your transaction when it detects an error. If you're looking for randomness, then unlike other blockchains whereby you have to actually use oracles for random data, you can use Harmony One's VRF, verifiable random function, which is a pre-compiled contract on the Harmony One blockchain, which will give you random, unbiased, verifiable, and immediately available random number per block. So every single block will have one random number that you can access. And it doesn't need additional fees. The code for this is here. You can just copy and paste it and you can use it. In Solidity, there's typecasting, so you can convert any variable to any other variable, and Solidity will do its best to try and convert that. There's a special address data type, which you can't do arithmetic on it. However, it does allow you to interact with other accounts in the blockchain. So you can send, receive, you can transfer, you can get the balance of any address on the blockchain. Different data types, there's also bytes 32, and string. String stores all its values in UTF-8, so unless you need that UTF-8 functionality, it's recommended to store it in bytes because UTF-8 is much more expensive and data stored on the blockchain is very, very expensive. There's also a var type, which doesn't have a type associated with it until you first assign something. So once you've assigned it, it will forever use that same type. Vars can also be used to capture functions. So just like in JavaScript, whereby you can have a variable pointer to a function, the same thing can be done in Solidity. And finally, most types can be deleted. When you delete it, it will set the value to 0, nullify it basically, and you will get a refund, a small refund on the amount of gas that was used to store that particular variable, especially if it's a state variable. Finally, you can also destructure your tuples like designed here. Now, if we move on to the data structures, there are only a few key data structures that are available in Solidity. You've got the arrays. They can be static arrays or dynamic arrays. Static array has a constant that defines how many elements are in that array. For a dynamic one, you don't specify the number of elements. You have functions that allow you to push and pop on that particular array, and you also can get the length as well. You can also define multi-dimensional arrays, whereby in this particular case, you have defined 5 dynamic array elements. Solidity also has a very special type called a mapping. It's really like a dictionary, or in JavaScript's case, like an object, whereby you can access the values by using a key value pair. So you specify the key, and then it will allow you to define a value. The only difference is that you can't actually iterate across this. There is a way to build data structures around this so that you store the keys and you also store the mapping as well. But that's a different discussion. Finally, you can nest data structures. So in this case, we're nesting a bunch of mappings. You can, like similar to data types, delete the data. Structures are just a convenient way to collect a bunch of variables so that you can form a logical grouping of these. It's cheaper than contracts and it makes your code a lot more cleaner. In the case of the example here, we have a bank who has an owner and a balance, and you can initialize the structure by using either the object notation here or by the order in which the variables appear in the structure. So in this case, we have address and a balance. You can also set the balance, so the new values, by just calling the object dot balance or object dot address, and of course you can delete it as well. Finally, Solidity has a type called enumeration or enums, and enums are a convenient way for you to restrict the valid values to a specific set of names. So in this case, for state, we only have created, locked, and inactive. Enums can be explicitly converted to ints by just doing the typecasting. Finally, we have data locations. We have memory, storage, and core data. All complex types like arrays, structs, they all have a data location. Memory does not persist. So anything that's in memory will be lost when the function call exits. You also have storage variables, which do persist. So any changes to a storage variable will persist across different multiple calls. So you can think of memory and core data as stack variables, which disappear after the function is returned, and storage as persistent storage for that smart contract. Most types you can explicitly set which data location to use. So moving on, Solidity also provides operators. They support a standard set of operators which are similar to languages such as JavaScript and C. So you've got arithmetic operators which allow you to add, multiply, divide, modulo, etc. You have relational operators which give you a Boolean response. So either equals, not equals, greater than, less than, etc. You have logical operators, bitwise operators, assignment, and conditional operators. These are all supported and their functionality is very similar to JavaScript and C. If you want to know more about operators, you can visit that link there, geekforce.org, Solidity operators. Solidity also has a set of global variables which are accessible by all function calls. There is this, which specifies the contract scope for which the function is executing. So you can use a dot notation to call functions. For example, this dot function, some function. You can also call this dot balance to find out how much one this particular contract has. You have the message variable, which gives you information about the calling function and its scope. So message.sender is who was the sender of that message. Value is how much one has been transferred to that if it was a payable function. Message.data is some arbitrary data that was supplied to that call. And message.gas is how much gas has been used. You also have access to something called TX or transaction. Transaction gives you access to origin and gas price. Now, the main difference between tx.origin and message.sender is that tx.origin is the original external account that started the transaction, while message.sender is the immediate account that invoked the function. So we'll go through that example later on. Finally, you have the block variable. The block variable tells you specific information about that particular block. The number, the difficulty, the block hash, gas limit. And there's also a special variable called now, which gives you the current Unix timestamp for that block. So let's have a quick quiz about global variables. Have a look at this smart contract and try to figure out what is the result when we call the get sender and get origin. Alright, so if you said get sender would return message.sender and get origin would return tx origin, then you'd be correct. Alright, so let's try a very simple example that represents this. So we just launch this up, we will see a few examples. The contract is very simple. First you have this call set sender and set transaction origin, which will actually call an internal function inside the call test that will set the message.sender and transaction.origin. So we're really just testing out a multi-level contract call and seeing the results. So what I'll do first is I'll quickly compile it and then I will deploy this origin via sender. And I'll make note of the address. So you can see the VS origin sender is 0xD91 and the account or the caller is 5B3. So if I go and quickly just set the sender and origin, if I was to call get origin, I'm expecting that this function will return me my account, which is 5B3. If I call get sender, I'm expecting this function to actually return the internal address of the address of the origin versus sender, because that is the immediate caller to that function. So if I was to click that, I would expect 0xD91 for sender and 5B3 for origin. So let's have a look. Yep, 5B3 for origin and D91 for sender. And that's because the different scope in which that function has been called for set transaction origin and set sender has caused core test to store different variables for the different context. Alright, let's move on. In Solidity, you can define functions which allow you to do certain business logic. So in this case, we're incrementing variables that you've supplied into the function by one, but you can do more complicated things as well. Functions can have multiple return types and function modifiers, such as returns, public, view, etc. View and pure functions are only executed locally, not on blockchain, and they do not change the state of the blockchain. So you don't send any transactions across to modify a particular variable. Pure functions are even more restrictive because they don't even allow you to read the state of the variables. If you try to read a state of a variable or modify a variable in a view or pure function, then this Solidity compiler won't even allow you to compile it. Function visibility specifiers allow you to control who can have access to that function. So there's public, external, private, and internal. I'll go into this in a bit of detail with some examples. Functions can only receive one tokens if they have the payable modifier. So if your smart contract wants to be able to receive tokens, you need to define a function that is payable. Solidity also supports events and modifiers. So events are defined in the smart contract, and they are fired from within the smart contract to notify all external listeners that something of interest has occurred. So anyone on Earth can actually listen to these events, capture it, and do something when that event is fired. You can also restore data that is persisted and immutable. It's stored along with the blockchain node. However, the data stored in this way can be queried by external callers, but not accessed by the smart contract itself. So any smart contract functions cannot access that data. Modifiers allow you to validate inputs to functions, for example, balance, the user authentication, etc. And it's very similar to guard clauses that exist in other languages. So let's quickly hop over to the examples and we'll just talk through some of them. So here are some examples of functions, modifiers, and events. The function construct has the keyword function followed by the function name, any arguments that you have, any function modifiers, and a return. You can actually return multiple values in a single call. So in this case, we are incrementing the x and y variable and we're returning that. You don't have to explicitly return those variables if you have a named variable. So if you assign x and y, then those values get returned to the caller. As mentioned, if the function is a view function, and let's assume that uint y is a state variable, if I have this code whereby y is incremented, an exception will be thrown and I won't be able to compile. This particular line will fail with the message saying something along the lines of this is a view function and you cannot modify a state variable in a view function. As mentioned before, pure is even more restricted. Function visibility specifiers allow you to define the visibility for each of the functions. There are 4 types of specifiers: public, external, private, and internal. Public specifiers are visible both externally and internally. So internal to the smart contract as well as external. External specifiers mark a function as only visible externally. So within the smart contract function itself, meaning within the smart contract that function resides in, other functions cannot call it. By default, functions are marked as public. A private specifier means that that particular function can only be accessed by the current smart contract. Derived contracts would not be able to see that. And that function is not externally visible. Finally, you have the internal specifier, which means that that function is only visible to the current contract and those that are deriving from it. Generally, it's a good idea to mark a function explicitly, and a lot of Solidity tools out there will actually raise an exception if you don't mark your function as one of these specifiers. If you want to receive 1 tokens when someone calls your function, you must mark that function as payable. Payable tells Solidity and the blockchain that this function can accept 1 tokens. Just a few side notes. It's preferable to use loops rather than recursion because of the max call depth of 1024, and because every single operation that occurs within a smart contract consumes some gas, and there is a finite amount of gas that is supplied to the smart contract. Another thing you have to be wary of is that you don't set loops which are unbounded, because eventually you run out of gas and that function won't be able to be called. So let's talk a bit about events. Events allow you to notify external parties that something has happened. It's really easy to search, it's very efficient, and you can store a specific amount of data in there. You can store data in there, and you can store data inside the event. So here's an example of an event. What we're doing is we are emitting the log send event from a specific function, and then here's some code that actually listens for that log sent event, and then console logs that information out. Finally, we have the function modifiers. These validate inputs to functions and are very similar to guard clauses in other languages. Underscore is usually used as the last line in the body, and it basically tells Solidity to execute the function. So it says if you don't have that underscore and you call a modifier, then nothing happens beyond the modifier. So here's some examples of modifiers. For example, for this one, we are checking that the time is greater than or equal to the current time. Only owner is a very frequently used modifier, which makes sure that only the owner of a smart contract can execute certain functions on that. Modifiers are also commonly used to control the state of a particular smart contract. So for example, if a smart contract has been initialized, then you can take certain steps. If it hasn't been initialized, then it will throw an exception and the modifier will return false. All right, let's move on. So we've learned about events, modifiers, and functions. Let's have a quick quiz. So what's the key difference between a public function and external function? You can pause now, give 5 seconds. A public function is visible externally and internally, meaning anyone can call it. However, an external function is only visible externally. A smart contract whereby one function is marked as external, other functions within that smart contract cannot call that, even with this notation. The best practice is, if a function will only ever be used externally and never be called within the same smart contract, then it should always be marked external. There are some gas cost savings, and it's typically a best practice. So what's the limitation of event messages, and why can't we use it to store data for our smart contract? So the answer is because the events are stored within the blockchain and are immutable. However, they can only be accessed externally. Smart contracts themselves do not have access to the stored events. So while we can store lots of data, we can't actually access it from the smart contract, but we can access it externally. Someone's actually written a choose your own adventure book using smart contracts and logs. So you can actually read the story from the logs themselves, and then you can make specific actions by sending transactions to that smart contract. A very interesting concept. And so let's talk quickly about branching and loops. All basic logic blocks work in Solidity. So you've got the ifs, you've got the whiles, you've got the fors. You can break, continue, and you can return. The only thing that's not supported by Solidity is the switch case statements. The syntax for these branching and loops are very similar to JavaScript, but with just one key caveat. There is no automatic conversion to bool. So I can't use a truth-like value, for example 1 0, to represent that boolean logic. You have to actually specifically say that b less than 0 or b greater than 0. and then specify that as part of the condition. Also, one thing to be wary of, because Solidity is using gas to operate, you have to make sure that user behavior is not used as a loop condition. Otherwise, the contract may run out of gas and never be able to successfully execute. So with that, let's have another quiz. So what are some issues with the code below? And I'll give you 5 seconds. You can pause the video if you want. The first issue is that the transfer function itself may actually throw an exception. And if it does, then your logic will never work again. So you'll never be able to call the function, and you'll never be able to, in this particular case, refund the address list. And that could happen. So if transfer failed, or if some malicious actor did something during the transfer operation, then this function could fail, and that loop will never be able to complete. Now the second problem, which we just mentioned, is that the loop could be arbitrarily long. So that refund address list dot length could be thousands of refund recipients long, and when you call this function, it will eventually run out of gas, because there is a finite amount of gas per block that operations can work within. And if it exceeds that max gas for a block, that function will never execute, and you'll never be able to send the transfers. So this brings up an interesting point. For these particular contracts, it's better to have individual people that within the refund list to withdraw their amount and then flag that as withdrawn, as opposed to having one function that does all the transfers and all the refunds. So this is called having a pull payment over a push payment. And what we're seeing here is a push payment. That's one of the best practices that are currently out there. So next, let's talk about objects and contracts. I'll just jump straight into an example. All right, this smart contract is called inheritance, and we will look at a few examples. There are 3 key things we want to talk about here. The first one is about calling external code. So in this particular case, the consumer wants to call the info feed. Now there are multiple ways to do that. Either you define your own info feed, which is what's happened here, we're creating a new one, or you can reuse an existing info feed. So basically, we're wrapping the info feed object, we're wrapping an address in set feed around an info feed object and treating that address as if it was the info feed smart contract. Now you have to be very careful, because 1, the constructor is not called when you do this, and number 2, we assume that address points to a valid info feed. If it doesn't, then Solidity will throw these really strange exceptions. So this particular function will allow you to then create a feed and then call the feed and pay some gas inside. So let's give it a quick go. So if we compile this contract, and then we choose consumer to deploy. Now what I can do is I can create a new feed, and then I can call the feed with some value, maybe 100 Wei. You can see just storing 100 Wei into this particular smart contract. So that's being able to call an external smart contract, and this type of pattern is quite common. So you have defined either an interface which represents the class, which represents the contract you want to call, or the contract definition itself, and then you supply it with the address, initialize it like this. You can start using that smart contract immediately within your contract. So let's have a look now at inheritance. So in this particular case, we have 3 contracts. A, B, C, and D, E, F are base contracts to which we want to inherit. My contract is the contract that we want to create, deriving from both A, B, C, and D, E, F. So in this case, we have an override function called Z, which both A, B, C, and D, E, F define. And then we ourselves have to actually override this function with this specific keyword. And we need to tell Solidity that we are aware that ABC and DEF have the same Z function, and we are overriding both of them. We can call Z directly, which is within the same contract. We can call abc.z, which will call the underlying base contract Z function for ABC. And finally, we can call super.z. What's important here is that the order in which you inherit the different base contracts is very important, because the DEF will override any existing ABC functions. So DEF's Z function will actually override ABC's Z function, but they are still accessible within the smart contract. So if you use the dot notation and call abc.z, it will access ABC's Z function. If I call super.z, I'm accessing the immediate parent's overridden function. It will actually take DEF's. It will actually take DEF's definition of the Z function. And we can just quickly test that as well. So I've already deployed it. I've already compiled it. So I just deployed my contract, smart contract. And if I was to expand this, if I call result, what I'm expecting is three values to be returned: cur, parent, and overridden. I'm expecting cur to be 99, overridden, which is abc.z, to be 42, and parent to be 32. So let's just call that and see if that's the result. Yep, exactly as we expected. Parent's 32, overridden is 42. The last part about inheritance is the abstract contract. So abstract contract, if you define a contract as abstract, you cannot create an instance of it. If you try to, the compiler will throw an exception. The whole reason to do that is so that people can't inherit from a partially defined smart contract. So if I was to try and deploy my abstract contract, I would just get an exception. Not implemented, yep, which is as expected. All right, let's move on. A very quick quiz. So, just the example before, what will be the result of calling my contract dot result? What are the three variables? What is cur, parent, and overridden? Give you 5 seconds. Or you can pause the video. The expected value is cur will be 99 because it is calling the current function within my contract. Overridden is calling abc.z, which is 42, and parent is calling super.z, which happens to be the more immediate parent that overrides z, which will be 32. So that's what we're expecting as the result. When you're overriding multiple base contracts with the same function signature, the last contract in the inheritance list will be used, in this case, def.z. All right, moving forward. Solidity has a whole bunch of other keywords as well. Here's an example of one of them, the self-destruct. Self-destruct actually destroys the existing smart contract and sends any one tokens that the smart contract was holding to the sum address, the address that you specified. Be very careful because it doesn't transfer any ERC721s or ERC20 tokens. It just transfers the 1 tokens to the specified address. It also removes the storage and the code from current and future blocks. So previous blocks still exist, but moving forward, that contract will no longer exist. Very common pattern is to have a check on the owner. So message.sender, the caller of this remove function, is the creator, then you can self-destruct. So one of the security issues that happened a while ago, it was called the parity hack. So in the parity hack, someone actually managed to get control of the parity smart contract because the set owner function was set to public. So anyone could call that function. So someone out there called the set owner function and then self-destructed the smart contract. When they did that, all of the Ethereum that was associated with that parity smart contract was lost. So you got to be very careful when you're using this self-destruct, especially if you have some checks around message.sender equals creator. And it's a very interesting read. do have a read of that, I think we link some articles there as well. All right, let's look at some contract design notes. We'll just go through some best practices for contract design. Just be wary that all data that's stored on the blockchain is visible to everyone. So if you store a magic number that you think can be hidden using the private keyword, that's not possible. Everybody can see everything on the blockchain. It's just when you use modifiers and you use visibility specifiers, it just controls code access and ability to modify. It does not hide the data. So with that, what you typically do is you obfuscate that data before when you save it onto the blockchain. You obfuscate it either through some cryptographic hash or some encryption standard. And when you put that information onto the blockchain, it's visible to everyone forever. So best not to put any sensitive information up there. For storage optimization, you have to be worried that writing any data to the blockchain is very, very expensive. So it's very important for you to plan your data structures very carefully and just write the bare minimum that you need for your solution to work, because it's infeasible to write everything onto the blockchain. One thing to note, as mentioned, controlling data access and function access doesn't actually stop anyone from reading what's on the blockchain and what's inside your smart contract. It really just prevents you from accessing and viewing it programmatically. But because blockchain is transparent and because blockchain is visible to everybody, anyone on earth can inspect your smart contract and see all the variables that are inside. Smart contracts execute within their own environment. So the smart contracts can't go out of the blockchain and retrieve data. So that's why we have these things called oracles. So to be able to supply data, external data, to your smart contract, you need these things called oracles, which will actually really is just a trusted source that is calling your smart contract and giving your smart contract specific data. These oracles can be run within a cron job, especially if you have time-based scheduling and you need to call your smart contract on a frequent basis. You can use a cron job. And finally, you can use the observer pattern, which is similar to publish subscribe, whereby you can have a smart contract call your smart contract when a certain event happens. So we'll just quickly hop over to some examples. In the case of obfuscation, what people tend to do is they can seal some data, which then they can reveal at a future time. So they may store a hash of the data onto the chain, and at a later time, they can provide the secret key and some bit amount to be able to unseal that information. And we mentioned storage contract optimizations, we mentioned oracles. The easiest way to actually use an oracle is to use the Chainlink data feeds. Chainlink has a lot of different data feeds, and you can just reuse them and point them to your smart contract. These are actually on-chain reference points, and they've been aggregated by multiple sources, so you can actually trust that the data is valid. Finally, this is an example of the callback code that we had mentioned before. So anyone that wants to be notified that something has happened will need to override this particular Oracle callback function, and an external party can then notify all of these different registered subscribers. So before we continue, what is a problem with this Oracle callback framework? All right. So this notify function, we mentioned earlier that really you shouldn't be calling an unbounded loop and then calling functions which may or may not throw an exception. So this notify could actually fail. You never know. One, either because Oracle callback throws an exception, or two, because the callback is unbounded and can execute beyond the amount of gas that's available. All right, so let's hop into the quiz. So why is it a bad idea to store sensitive data unencrypted on the blockchain? I'll wait 5 seconds, or you can pause the video. The reason is, you can mark a state variable as private, but it doesn't prevent anyone from actually looking at the block and then reading that data itself. Private prevents our contracts from reading it, but anybody that has access to the smart contract can still read the block and the underlying data. So just be aware that all data to start of time is stored on the blockchain, and anyone can actually look at the data, look at who's modified the data, and look at the state of the data across time and its life cycle. So that's why blockchains are very useful for traceability, tamper-resistant systems as well, because you can change the data on the blockchain, but people can still see who changed it, and they can see when it was changed, and they can see what was the value before the change, and you can't delete that. Right, so here's some other useful functions that you may bump into in your day-to-day offering, in your day-to-day programming. We have currency units, and these are just convenience functions within the smart contract to allow you to convert or to specify one Wei, one Ethereum, one Gwei. Originally, there was two other data units, Fini and Sabo, but these have been removed as of 0.7.0, so just be aware of that. You also have access to time units, so you have seconds, minutes, hours, days, and you can do maths on these time units as well, because they're really just stored as Unix timestamps. So really, they're just stored as a special variable which represents time. Finally, you've got this access to precompiled cryptographic smart contract functions, SHA-3, RIPE-MD160, and SHA-256. These are just hashing functions that make life a lot easier. So you don't have to, define your own SHA-3 to SHA-256 functions, because they're built into the blockchain itself. So let's talk quickly about security. Bugs in smart contracts written in Solidity can be disastrous, and even popular patterns that existed can turn out to be anti-patterns with security vulnerabilities. The biggest one, in fact, and the most famous one, is the DAO attack. So the DAO was a re-entrancy attack which allowed an attacker to keep drawing funds until they withdrew all the money which was in a smart contract. And the reason that happened was we did a transfer before we did a state change. So the balance of a particular wallet was checked only after the transfer had happened. And if you had wrote a very specific code, you can actually re-enter and keep drawing funds out until the contract runs out of funds. And that was attacked very early on in Ethereum. And that's why we have that split between Ethereum and Ethereum Classic. So there's a list of security related articles at the end of this document and the accompanying tutorial. Do suggest you read it, because it talks about security, the mindset of writing smart contracts, and in tools that you can use to make sure that your smart contract is resistant to a lot of the common attacks. If you want to read more about the different hacks, just hop over to the history of crypto hacks from this Medium article, and it will talk about all the different hacks and all the different exploits that have happened since, I guess, the start of time. Finally, let's talk a little bit about the low-level functions that are available to you as a smart contract developer. In this example, there are two that we can talk about. There's call and the call code. Call is low-level, but it's not really used frequently because there's no type safety. So if you look here, we can call this function name and specify arguments. We don't know what those arguments are, and we just call that function without checking if the variables, the type, are valid. There's also call code, and call code allows you to execute within the context of the calling contract, and it's useful for doing libraries. So for example, if I have a function called A, and I want to use another function called B, I can use call code to make it so that any operations that B does directly impacts my internal state of the contract A. So A's contract state can be modified by function calls within B. So you got to be very careful here, because malicious smart contract can actually screw up your state. Finally, let's look at a demo just that puts all of this knowledge and all of this information that we've discussed into practice. All right, so this smart contract is called Crowdfunder, and really it's just a crowdfunding example similar to Kickstarter. So you specify the Solidity version, and it's just a simple contract which has a few variables: the owner, who is the beneficiary or the receiver of this fund, the minimum amount that you want to raise, some nice campaign URL so people can see what's happening in the campaign, and a specific version for this. So we've got some data structures. In this case, it's an enumeration which really controls the state. Is it fundraising? It's expired, it's successful, etc. And we have another structure called contribution, which keeps track of the amount that a specific contributor has paid. A few state variables around the state: total amount raised, how many people raised it, and when was this completed, and all the different contributions. Contributions itself is a dynamic array. We also have a bunch of events: the log for funding received and a log for the winner that's been paid. And finally, we've got a few modifiers to check whether the state matches what we're expecting, whether the caller is the owner of the contract, and whether or not we are at the end of the life cycle for this particular crowd fund. So we're looking at the function called crowdfund. What you're doing is specifying the amount of hours that you want the fundraising to run for, the URL that people can browse to read more about the campaign, who's receiving the fund, and the minimum amount that you want to raise. All of that is stored as state variables within the smart contract. Moving on, we also have a function called contribute, whereby anyone can actually call this to contribute some amount. The only way you can contribute is if we're still in the fundraising state, and for every single contribution that happens, we store the contribution details, and then we increase the total raised by the value that was sent to the smart contract. So this allows anyone to donate however much money they want. It's not a fixed amount, and we are just keeping track of how much has been donated. Not only that, we also emit a log to tell everybody on Earth that this particular sender sent us this amount of one, and the current total raised is X amount. Finally, we do some housekeeping to check if the fund was completed. Total raised matches the minimum to raise, and that's what that function here does, which is just to check if the funding is complete or expired. And finally, we return, in this particular function, contribute, the ID, which is really just an index of where that contribution happened in the array. We do a bit of checks on the keywords now, so just seeing if the value of now is greater than raised by, so when you're expected to meet the target. If it is, then we flag this crowdfund as expired. It didn't meet its target. If it did meet its target, we call this function called success, and we do a payout. And really the only thing the payout does is it makes sure the state is successful, and then it transfers the total amount in this smart contract to the fund recipient, and it will log a message saying that the fund has been dispersed. At any point in time, you can get details of a particular contributor by giving the ID, and at any point in time, you can actually also remove the contract, which self-destructs and sends all the money through to the contract owner. Now, I'll leave you with a few words. Maybe you can go through the smart contract and try to figure out what are some of the vulnerabilities or some of the issues that you can see with this particular smart contract. Is there any way for me to, say, change the owner, modify some of the variables? Is there any specific checks that are missing? Is there a way for me to circumvent some of these internal checks and modifiers? And if there are, what are some things you can do to improve the smart contract security? All right, with that, we've come to the end of this tutorial. Thank you for your time, and stay tuned for more. Here's some interesting links to some of the Harmony One initiatives, tools, community, and even solutions as well. So visit the Harmony One website and continue learning. Thank you for your time.